Hello everyone, welcome back to Math with Allison. Today we're continuing our series on derivatives. If you haven't already, I have a little introduction to derivatives right here. Click that little eye in the corner and it'll get you there. Otherwise, we're going to be going into the limit definition today and what that looks like. So let's go ahead and dive into it. Question of the day. Can we find an equation for the slope of a function's tangent line without having to use a point? So let's go ahead and look at these different tangent lines. I have a couple points filled out already. If I look at the point 2, 4, and I drew that tangent line, it would look exactly like this, right? And now if I go to the point 1, 1, I will have a tangent line that just skims it at the point 1, 1. And so my slope changes. At 0, 0, I would actually have a horizontal tangent line. At negative 1, 1, here I would have a negative tangent line. And then same thing for negative 2, 4. That is how I would draw that out. So notice how our tangent lines move according to which point we choose. So the slope of the tangent line for any function f is a function itself, and it's called the derivative. And we have the limit definition of a derivative right here. We have the limit as h approaches 0 of f of x plus h minus f of x all over h. So we denote this with f prime. That little f prime notes the derivative. And notice we were originally in our last video looking at specific values. So we would look at a specific value a. Now this works for any value. That's why we just use x. We don't need to use a anymore. So I have an example right here on what does this actually look like. I have a value x with its corresponding y value f of x. Now I added a little distance of h, and so now I have a new x value, x plus h. And I have the corresponding y value, f of x plus h. We can think of this as change in y over change in x, right? If I take my first change in y, I have f of x plus h minus f of x, and then this whole thing is going to be all over the change in x. So I take x plus h and I subtract x. Notice here how my x's actually cancel out. And so now I just have f of x plus h minus f of x all over h. And this is exactly what was inside our limit. So we're doing change in y over change in x, which is similar to slope, but we're taking the limit as h goes to 0. So as this distance right here gets smaller and smaller, that's going to define an equation where we can find the slope of any tangent line. I can just plug in a value and boom, I have the slope. So let's go ahead and see an example of this. Let me zoom in a bit. We have f of x equals 1 minus x squared, and we have an a value of negative 1. That's going to help us for the second part when we find the tangent line. But our first order of business is to just find the derivative, and we're going to go ahead and use the limit definition. So I'm going to go ahead and plug in what I know. So I have the limit. Now, when I plug in f of x plus h, I'm changing my input. So my input changes from just a value of x to x plus h, which means I'm going to square that input. So that becomes 1 minus x plus h squared. Minus f of x, so minus the original function. So I'm going to subtract all of 1 minus x squared. And then this whole thing is going to be divided by h. Let me go ahead and simplify that out. So notice here I had to distribute this minus sign to both the 1 and the minus x squared. So that became a negative 1 plus x squared. And now I'm going to go ahead and do the same thing here. I need to distribute that minus sign to all terms. So once we get this part completely simplified out, we always want to look for terms that are going to cancel out. That's usually the point of this, is we get stuff that cancels. So here I notice my 1 and my negative 1 cancel out, along with my negative x squared and a positive x squared. I'm going to go ahead and rewrite this. Our next order of business is we always try to get rid of that h in the denominator, because that's our issue value. We can't just plug in 0, because then we're dividing by 0 and that's super illegal. Usually we get to a point where that h can divide out. And here we see that it can. If we factor in h out of the numerator, I'm left with h times negative 2x minus h all over h. And now I can see that these h's divide out. So I'm going to rewrite my limit. I got rid of my issue, and now I can go ahead and use direct substitution. So I'm going to plug in that value of 0, negative 2x minus 0, which is equal to negative 2x. So this is the function to find the slope of the tangent line at any single point. And we're going to go ahead and use that to find the equation at x equals 1. So this is going to also be my a value. A is equal to 1. So in order to find my slope, and I'm going to write m is equal to my slope, I just get to use my equation right here and plug in the x value. So I get negative 2 times 1, which is just equal to negative 2. And now I'm going to use the equation of a line. I'm going to go ahead and write that out. So notice here we found our m, and we also have our x1 already, but we need to find our corresponding y1. And that's when we go back to the original function. Our original function was f of x equals 1 minus x squared. And I can plug in the value x equals 1 to get my corresponding y value. So y1 is equal to 1 minus 1 squared, which this is equal to 0. So now I can go ahead and plug everything in. I get y minus y1, which is 0, equals negative 2 times x minus 1. When I simplify that out, I get y is equal to negative 2x plus 2. And now I found the tangent line at the specific point. And so that's how we can use the derivative to find a general equation for all the slopes. Let's go ahead and see another example. So there is another method that we can use to solve for this where we break it up into different parts rather than doing it all in one. So we are given the function f of x equals 1 over x plus fine, and first we're being asked to find the first derivative. And so we have the limit definition written out here, but I'm going to go ahead and break it up into different parts. So we have a new input, x plus h, and I'm going to replace that in my x in my function. So I get 1 over x plus h plus 5. So this is my f of x plus h. Our f of x doesn't change, so I get 1 over x plus 5. But now I'm going to do some algebra in this next step. So I'm going to rewrite these. Notice I left some space, and that's because I want to combine these into one fraction. This is the type of example when we have a fraction as a function, and I always suggest creating one common denominator so we can combine them. So in order to do that, I'm going to multiply this fraction on the left by x plus 5 over x plus 5. And then I will also multiply this one right here by x plus h plus 5, and the same thing in the denominator, right? This creates a common denominator. I'm going to go ahead and write this out. So now that I have a common denominator, I can go ahead and combine these two fractions. So I get x plus 5 minus the entire second one, x plus h plus 5. Don't forget that minus sign means we're subtracting each individual element, so I have to distribute it. So when I distribute it, I go all the way through, and now this becomes, and like I said earlier, usually things are going to cancel out. That's the nice part about this. So we get the x minus x, and we also have 5 minus 5. So if I rewrite this, I have negative h all over that whole denominator. So now I want to plug this into the limit. We already did the numerator, and now we can plug this in because this whole thing is going to be over h. So this is a lot going on. There's a lot of fractions. This is how I like to rewrite it. I like to pull out that division sign, so I get negative h all over. But I'm going to say now we're divided by h. So I just rewrote the fraction. But remember, when we divide by h, we can multiply by the reciprocal. So this becomes 1 over h. And this is how we get rid of that issue, because that h divides out. And so now I'm left with a limit. And now I can go ahead and use direct substitution. So when I plug in that h value of 0, I get x plus 5 times x plus 5. Or if I wanted to, I can rewrite this as negative 1 over x plus 5 quantity squared. And so this is the equation that I can use to find the slope of the tangent line at any point. So here we're not going to find the tangent line. We're going to move on to a new problem. We're practicing the limit definition, so now we have a square root type of function. So I like direct substitution. If you like the previous method we did in the last problem, totally up to you, whatever your heart desires. I'm going to go ahead and plug in what I know here. So the limit as h approaches 0. Remember, my new input is x plus h, and so that's going to replace my x there. So instead of 2x, I get 2 times quantity x plus h plus 1. And I'm going to subtract the original equation, which is 2x plus 1. And all of this is going to be divided by h. I'm going to go ahead and simplify this out a bit. So when we have square roots, the method that I suggest is multiplying by the conjugate of wherever the square root is. So what I mean by the conjugate is I take the terms remain exactly the same, so 2x plus 2h plus 1. And the same thing with the other term, 2x plus 1, but instead of subtracting, I'm going to add. So you just flip the sign that's in the middle. But remember, we can't just multiply out of thin air, so I also have to multiply the denominator by the same thing. Okay, so notice when we multiply these out, when I multiply these first two terms, they're the exact same thing on the inside of the square root, and the square roots cancel out. So here I'm going to go ahead and write this out. Okay, that was a lot to squeeze in there. But I wanted to multiply the whole thing out so we could see the purpose of multiplying by the conjugate, which is that these middle terms, whatever the square roots are, they cancel out. And we're left with values that are not square roots anymore. Notice that I didn't simplify out the denominator, and that's because I don't really care to. It doesn't really do anything special, and I don't want to waste math power on it. So I'm going to go ahead and rewrite this. Okay, so first I had to distribute this minus sign right here, so I distributed it to the 2x and the 1. And so now this is what I'm left with. Like I said, usually things cancel out, and so I have 2x minus 2x plus 1 minus 1. So now notice here, all we have in the numerator is a 2h. And usually the h divides out, and the h is our issue. So here my h divides with an h, and now all I'm left with is a 2 in the numerator. So I'm going to rewrite this. And that's why I don't suggest simplifying out the denominator, because things like to divide out. So we got rid of our issue, which was that h in the denominator, and now we can use direct substitution. So when I plug in h is equal to 0, this is what I get. And I can actually rewrite the denominator, so I get 2 over 2 times the square root of 2x plus 1. And actually, we can continue simplifying this because those 2's divide out. And so now what I'm left with is 1 over the square root of 2x plus 1. And that is our derivative and also our function we can use to find the slope of the tangent line given any x value, any point. So this is all I have for us today. If you enjoyed this video, please leave a thumbs up and comment other topics, problems, or content you'd like to see done. Thank you so much for watching.